based on your experience from midterms 1 and 2, the practice problems with the higher numbers are the ones that you want to really use as practice for the exam. And then sort of lower numbered problems will be those that test relevant concepts, but the format of those problems will not reflect the format of the final. And basically the final is going to look similar to midterms 1 and 2. It is cumulative. It will include stuff that, or stuff from this most recent module. It won't ask you to like do a lot of complicated math. But it may ask, it may show you kind of mathematical or algorithmic formulations of analysis problems you have not seen and ask you to translate that into code. So being familiar with all of the notebooks kind of in this latter third of the class will be important. And we will probably for next time, we'll do a practice. I'll try to do 2 practice problems in the next session that give you a very concrete sense of what that really means. Like what is the level of sort of mathematical fluency and algorithmic fluency in this last section of the class are we looking for the final. Okay, and all right. Okay, so topic 15 is related to something that I think we did a poll in one of the earlier classes. I asked people if you had seen principal component analysis, and I think the answer was everyone who responded to the poll, the answer was yes. So for people in the audience, just a show of hands, how many of you are kind of familiar with principal components analysis? Okay, good. So I will show you, so I'll just sort of sketch one way to interpret or motivate the PCA problem, which will lead us quickly to computational methods, and then we can sort of focus on the computational methods themselves for actually calculating PCA. And it boils down to some fundamental linear algebra, something that I think a substantial fraction, but not a full class, had said they were familiar with, which is the singular value decomposition. And I'll make some meta comments about that as well. Okay, so the way I'm going to motivate PCA is maybe a little bit different than what you might have seen in some other experience, and that is through the lens of data compression. And through this lens, the idea of a parametric model of some data set is, in a way, a kind of way of compressing the data set so that you don't have to represent the data set itself, or you don't have to represent the full data set. So this is the connection to compression. And we're really motivated by compression for a couple of reasons. So one is we just want to save time and space. So for example, let's say I have an image, and this particular image is, however many pixels by however many pixels. It looks like there's a total of maybe 6 million pixels. So in the full representation of this image, there's 6 million points, if you will. And the idea of data compression is we take this image and we somehow replace it with something that at least visually looks like the original image, but doesn't require storing all of the points in that image. So, we will talk about something called the truncated SVD. So just a sort of quick show of hands, how many of you have seen the truncated SVD before in some class? Okay, good. So only a couple of you in the live audience. So the truncated SVD, which gives us a way to calculate PCA, principal components analysis, just more generally is a way of, you could think of it as a way of reparameterizing just any matrix. So if I take the image on the left and I view it as a matrix, so a matrix whose entries are the pixel intensities, then the truncated SVD gives us a way to factor this matrix into a special form that we will describe today. And that special form gives you it has a tuning knob in it that lets you kind of dial up and down kind of how approximately you would like to represent this matrix using fewer parameters. So you tune this knob that controls how many parameters are used to represent the actual image. And here in this picture, hopefully, well, if you look really closely, I think it's debatable how good a representation of the original image this one is. But here is a particular setting where we can compress the size of the image by a factor of 10 with only a 10% error in some measure. So we'll talk about what that measure is momentarily. Okay, so this is what the thing I want to emphasize at this point is I will describe PCA in a way that is similar to what you have seen in other places, but our description will lead us to an algorithm. In order to run the algorithm, we will use the idea of an SVD, a singular value decomposition. But that tool of the SVD is more general than just its use in solving PCA. In fact, it's sort of like a Swiss Army knife for linear algebra problems. And one of the practice exam problems we'll do on Thursday, we will invoke the SVD again, just as a sort of reinforcement or as a check on how well you understand the way it works or how it's used. Okay, so I just wanted to use this as kind of setup. There's a tool, there's a more general tool here than just PCA that we will talk about. Okay, so there's some. So sometimes we have data, we want to make it smaller, we want a smaller representation via some model or some approximate representation. Another way to think about compression is if something is compressible, then that means there is some underlying structure there that you can exploit in order to use essentially fewer bits to represent it. Okay, so for example, in the image, what would be an example of structure here that you see that just conceptually would allow you to reduce the size of the representation of this image? Just what's any structure that you see?
Like the grayscale that it's printed in be a structure?
So the fact that it's in grayscale it's a property of the image that you might exploit somehow. How would the fact that it's in some grayscale allow you to come up with a smaller representation?
You could blend some of the colors.
Okay, yeah, good. So in grayscale, there's kind of there's a natural progression from dark to light. And there is a natural notion of two colors being kind of close to each other versus far apart from each other. So if you can identify any substructure that kind of groups nearby colors, then one way to approximate the exact colors would be to replace them with something that's like a nearby color. Okay, so you could see, so for example, here's a big, so I've superimposed artificially this, square grid, sort of broken this up into little rectangles. And you can see in this rectangle, most of the pixels have the same color, or it looks the same. So rather than, for example, storing this entire, all of these pixels, you could just store, say, one color, which is maybe the average color in the square, as well as the size of the square. And that is already a much smaller representation of just that section. Okay, and that's an example of structure. What are other structures you see that might be exploitable in some way? You don't have to know exactly how. Just what would your ideas be?
Could it be the different shapes in the?
Okay, good. Yeah, there are natural geometric shapes that appear. There are things that look like triangles. There are things that look like letters, right? Actually, in fact, if you knew what the font was or what the typeface was for the word tech, then you would just store, oh, there is the word tech in this font that's skewed in a certain way. Like there's some other representation, some other way to describe what is printed there that maybe some magic thing could extract, and you could use that. as an alternative way to describe this image. Okay, and there are lines, there are other kinds of squares, there are things that are rectangles that are kind of skewed in some way. So there's there's geometric structure in the image as well that you would like to exploit. Okay. Okay, good. So this is so in that sense, the idea of compressing something you could also view as a way to uncover or exploit some underlying structure. So let me give you a different example, which is motivated directly by PCA. So there's I don't know if, have any of you seen this website, this Explained Visually website? It's kind of a cool website that discusses various topics and just some simple topics in data analysis and in linear algebra through visual examples. And one of the, in the description of PCA, you're given this particular data set. The data set is described as consisting of 4 data points. And the data points correspond to the 4 panels that you see. And you can see from the x-axis labels that are highlighted, each of the data points corresponds to some feature or some measurement or measurements made for a particular country, in this case, a country in the United Kingdom. Okay, so there's England, Northern Ireland, Scotland, and Wales. And each of these data points, there are these bars, and the bars are measures of grams per week of consumption. And what is being consumed, well, those are the features that you see kind of listed on the y-axis. And these are different like food, drink products of various kinds. So every country is a data point that is 17 dimensional. That's the number of features you see on the left. And the features measure average grams of consumption in this country based on some study. Okay, so if you just kind of sit back and you look at the bars kind of at first glance, I hope you'd agree that they kind of look the same. There's something here that appears uniform. At the same time, if you're trying to compare these data points, it can be a little bit challenging because you have to, like, for each of these 17 dimensions, you've got to like go across the data points and ask, okay, are they the same or are they different? So if there is any structure here that would separate the countries in some way, it might not be so easy to find just by inspecting sort of the raw features. So one thing you might then, and part of the reason why is, well, you know, there's, even though there are only a few data points, these are high dimensional data points. And because the data points, at least visually, look so similar, you would expect that if there are any differences, if there are things that kind of distinguish one country versus another based on their diet, you know, measured in this way, then there are probably small differences. And you would like to know, you know, or a natural question you might ask is, well, is it maybe just a few of these consumed products that lead to some kind of separation between the countries that sort of tell you that the diet of one country is measurably different from the diet of another? So that might be a thing you ask. Okay, so the tool of PCA gives you one way to try to answer this question, and it turns out if you kind of run a PCA on this data set, then what you can identify is a lower dimensional representation, in this case a 2D representation of that original 17-dimensional input, where there is some clear separation. There's some grouping that emerges once you do this kind of projection from the original space into a lower dimensional space. Okay, and so here, you know, Northern Ireland kind of sits apart in some way. And you can go back and ask why, and inspecting the principal components gives you a way to kind of then go back to the original features and ask, well, is there a subset of these that somehow that kind of explains the main difference resulting in a separation of, say, Northern Ireland on one side of this strange coordinate system that we've plotted the points on versus the other 3 countries. Okay, so this would be an example of identifying structure. PCA gives you a way of looking at that structure, but a different interpretation of what we've done is we have essentially done some form of compression. So we've taken 17-dimensional inputs and we've converted them into 2-dimensional representations. So we've kind of compressed away the original input features, okay, resulting in a smaller representation of each data point. Yeah.
Do the values have any meaning, or it's just
good question.
Say different,
yeah,
not based on what we see.
Okay, so great question. So the question is, well, the values. So we've taken the 17-dimensional points, we've transformed them into a 2-dimensional coordinate system. And what do these coordinates mean? Can you interpret them? And the answer depends on your point of view. So there is a kind of fuzzy way to interpret them, but it's not completely satisfying. So does anybody have a sense of why I would say maybe it might not be satisfying? So here are the original inputs. Measurements are in grams across these different categories. I then plotted into this space. What sort of things disturb you about this transformation? Yeah.
Well, so when you get PCA components, can't you kind of not tell, you know, it's like a recipe of some of the factors, but not exactly how much of each factor? You can kind of like estimate by the significances, but you're not necessarily certain.
Yeah. So the question is, I think what you're alluding to is, well, this transformation, what exactly are the steps involved in the transformation? That will be an important question to ask, and we will walk through that process to say, during that process, is there any step that then becomes hard to interpret? So that's maybe one, that would be maybe one thing about this transformation that might bother you. The second thing I think you allude to in your response are the values themselves. So if I look at, for example, the scales of the values, they seem to be on the order of magnitude of the original kind of input features, but you also see negative values here. Everything we measured initially was non-negative, right? These were grams, and now somehow we have negative values. So that should also give you some pause. Like, if I'm going to go back and reinterpret this in some way, what does a negative value mean? Okay. Okay, good. So whether we can interpret this, we'll do like a little. We might start it if we have a little bit of time today, but most likely we'll do it in the first half of the next class, and it will be about this interpretation question. Okay. Okay, so just moving on, I'm going to start with the second problem, this dimensionality reduction problem, and kind of how we can take PCA and think of it as a dimensionality reduction method. So taking high dimensional data and reducing it to some low dimensional representation. And the main assumption there is that there exists a good low dimensional representation. Okay. So for example, if we were to go from a 2D representation to a 1D representation, here's an example of data points in 2D. And you can kind of see there's some clustering. It looks almost like a regression problem, right? There's some clustering of these points that appear to lie on something that looks like a line that cuts through this space. Okay, so it's 2-dimensional, but kind of visually you could imagine, well, if I wanted to compress it approximately, then I could replace this 2-dimensional structure, these 2D coordinates, by just a single coordinate, which is some coordinate with some transformation of the original points onto this red line. Okay. So we're sort of saying, so the 2D to 1D example visually or schematically would be like, well, I have 2D input points, and now I'm imagining a new space which is only 1-dimensional. There's only one axis, and I want to move points and their positions on the left-hand side into something on the right-hand side that somehow preserves some some aspect of the original data points. Okay. All right. So to as a first step, since the points can kind of lie arbitrarily in this space, I'm going to do an initial transformation, which is I will mean center the points. So take the average X and Y coordinates, and then subtract them from the original data points, right? And so the result then is that so I will take the original points and then I will, subtract their mean vector, so that the overall mean is now the origin. Okay, all right. So we'll shift everything first. And then we'll think about this problem of going from 2D to 1D with respect to this mean-centered version of the data. So just in thinking about the steps, so far we've done one step. If you wanted to go back and interpret, as long as you maintain the original mean vector, going from this version of the data to the original, that would be easy. You would just add the mean back in, and that would get you back into the original space. So far, mean centering, it's not really anything that loses information. It's just something that, well, you'll see why we did it in a second. It's something that kind of moves all the points so that they're kind of centered about the origin. And when we center them at the origin, we can then interpret the points themselves as vectors. So we will treat all of these points as vectors. Okay, so for example, if I take one of these points in this kind of mean-centered space, it has a pair of coordinates, and those coordinates I will interpret as a vector. Okay. Now this vector, with respect to this kind of red line, so I'm sort of imagining that, so what my goal will be to determine the red line, like what is the red line? And so as a first step, I've done this mean centering. After the mean centering, I'm going to interpret each of these points as a vector. And I now want to represent the vector not in this original 2D space, but in the one-dimensional space of the red line. Okay, so the red line is also can be represented by a vector, and in particular a unit vector, a vector of length 1, that runs parallel to the line itself. And this is this is just like in the original 2D space, I represent the axes by their unit vectors as well, right? So I associate a unit vector with respect to each axis. So in this transformed one-dimensional space, I'm going to think of this red line now as a new axis, and I'm going to represent it by a unit vector, which I'll call phi, and the coordinates of phi will have some representation in the original 2D space. Okay. And if I now want to compress the sort of 2-coordinate representation of say this data point in this one-dimensional version, then I need to identify a point on this red line that will correspond to the original point, kind of in the blue, the original blue point. Okay, so a very natural mapping is, well, I just think of this as a, if I'm thinking of this as an axis, in the same way, if I ask, well, X, what is its representation in the A0, A1 space? Well, it's just the projection of the point along the 2 axes, and I measure the length. Right, so the point X in the figure, it has some coordinate, which is its length along A0, and another coordinate, which is its length on A1. Okay, so with respect to this new red line, I could ask, well, what is sort of the the length of this vector along the red line, and that would just be an orthogonal projection of x onto the red line. Okay, so if I do an orthogonal projection, that gives me a point, and the distance along the red line to the brown point is sort of its coordinate, is the coordinate of this point in the red space. Okay, so, or just, you can just think of the length of the component of a vector in this space. All right, so that is a projection. And you can, if I want to know, well, what is the length of this projection? So if I'm given the vectors x and phi, and I'm given their coordinates in the original space, then the length of this projection, it turns out, is x transpose phi, under the assumption that phi is a unit vector. So phi has length 1. It has Euclidean or 2 norm length equal to 1. Okay, so if I just do x transpose phi, given the 2D coordinate representation of phi and of the original point, then the length of this brown vector, so the length along the red line, is just x transpose phi. Okay, so that's just a linear algebraic fact. Okay, so any questions about what we've done so far? So we have original 2D points. We're looking for a 1D representation, which is this red line. The way we will characterize the red line is by, some vector that is parallel to that line, a unit vector. And if I want to know what is the representation of the 2D point on the red line, it's just x transpose phi. Okay, so far so good. We're good. Okay. Okay, so what red line should we choose? Well, a very natural idea is let's project all of the points onto the red line, and let's try to pick the red line that maximizes the total projection. So the projection of every point onto the line. And the idea here is, well, that projection, its length, it's going to be some fraction of the length of the original point. And we'd like to preserve those fractions as much as we can, okay, among all the data points. Okay, so so the red line I'm looking for is represented by this vector phi. If I take any data point, let's call it x hat sub k, so the kth data point, and I do x hat k transpose phi, that will give me the length of the projection of the kth point. So the thing I would like to maximize is essentially the sum of these lengths. And in part, and you would like to maximize some sum of the function, some function of these projections. And just like in linear regression, where we had, when in our description of linear regression in this class, we use this kind of ad hoc measure of, we'll measure these residual errors and we'll sum their squares. We will use a sum of squares measure for of these projections as well. So the function I'm trying to maximize is project onto phi, measure the length of the projection, square that, and then sum all of those. And that will be my measure of kind of the total projection, which is the sum of squared projections of all the points. All right, so I will use this as my function. And so why would you do this? So an ad hoc justification might be, well, points that have large projections, maybe you'd like to preserve those, and things with small projections are kind of small anyway. And so to sort of penalize getting the long vectors wrong, we will use this square. That might be one kind of justification. And it turns out there's also a statistical justification, which we'll see in just a second. But for now, let's just take this as some measure of projections that we'll try to maximize. Okay. All right. So so the task now is let's find a phi that that maximizes this function. And this stuff out front is sort of similar to this factor out front is just a constant. So it doesn't. It shouldn't affect. So it shouldn't affect the solution to the problem, and we will pick it. We're picking it essentially for aesthetic reasons. So we're gonna, when we go and minimize this thing, we're gonna get some formulas, and formulas will be cleaner if we use this particular constant. But it's just a constant, so it doesn't change the maximization problem. Okay. All right. So okay, so okay so far? Just okay, so I'm gonna, this is a kind of a vector version of this formula. I'm gonna replace it with a matrix representation. And for that, I will introduce this matrix capital C, which is X. So if I take my usual data matrix, so I've taken the data points, I've mean centered them. And then I get this sort of mean-centered data matrix X. If I calculate X transpose X and divide by M, M is the number of data points. This is this matrix I'll call C. So a mean-centered data matrix that I then, to which I then calculate 1 over M X transpose X. This is an object. This is also a statistical object. Does anybody recognize it? What object from statistics is the matrix C? Okay, so the object is, it's the sample covariance of the data. So that is so this particular function I've written down to maximize has another interpretation that's a statistical interpretation, and it's related to preserving or maximizing variance. So so the statistical interpretation, this is probably if you've seen PCA before, I'm assuming that's the kind of flavor of it that you've seen. Oh, you pick axes that somehow capture the variance in the data. So under this assumption that the data comes from like some Gaussian distribution, so it looks like a ball in its original input space, then we'll try to pick axes that sort of capture the axes that represent the ball, or sorry, not a ball, this sort of ellipsoid or hyper-ellipsoid thing. Okay, so this picture, so an ellipsoid, you know, that generates this might look like this round curve that I'm sketching. And you can see this round curve, if it's an ellipsoid, has kind of a long axis that goes along the red line. Okay, so that's another way to interpret what PCA does. Okay. All right, so returning to the problem itself, so this formula I've written down, this is a matrix formula, and when I evaluate it, I get a number, and I'm going to try to pick a phi that maximizes that number. Okay, so that's my mathematical goal so far. And when I have done that, I will have found the red line. Okay. All right, so here's that problem restated. So given this definition of J, I want to pick the phi, we'll call it phi star, that maximizes J of phi. Now there's another kind of technical bit we said, which is this vector phi should have unit length. So the 2 norm of phi should be equal to 1. So this, and it will be equivalent to express this constraint as the length squared is equal to 1. So this is asking for the same thing, basically. So I'll replace this constraint by this one. And of course, the length squared can also be written as phi transpose phi. Okay. And this constraint is an equality constraint. So that means the optimization problem I'm trying to solve is, maximizing this function of phi subject to phi transpose phi is equal to 1. That the vector is a unit vector. Okay. All right. So if I want to solve this optimization problem with an equality constraint, there is a trick that you may have seen in an optimization class that you're either taking or will take, which is called the method of Lagrange multipliers. And basically the way it works is instead of maximizing this original function, we will maximize a surrogate. And this surrogate will have extra parameters with one parameter per equality constraint. Okay, and I will introduce, and the way that the equality, and I will stick the equality constraint into the surrogate objective, essentially by rewriting the constraint in the form something equals 0. So remember, the constraint was phi transpose phi equals to 1, so I can write that as 1 minus phi transpose phi, for example. And then, so I'll just shove that as a term of this surrogate optimization function, along with a dummy parameter, which here I'm calling lambda. Actually, what I've injected is lambda over 2, and that will turn out to be for aesthetic reasons. But just, there's some constant. And then I will maximize this thing instead. So I'm going to maximize not j of phi directly, but this surrogate j hat of phi and this funny extra term. And if you had more equality constraints, you would just add them in the same way with additional constants. Okay, so that's the method of Lagrange multipliers. And how does that help you solve the original optimization problem? You'll see in a moment. Okay, this parameter lambda that I've introduced, that is a Lagrange multiplier. So that is the name of this parameter. Okay, and the constraints, we've seen that. Okay, so all right, so this is my new objective. I'm going to maximize this surrogate, and I'm going to find the parameters that maximize it. And of course, when you maximize, what do? Well, you're going to take all these partial derivatives with respect to all of the free parameters. So in this case, the phis and this new dummy parameter lambda. So you'll take derivatives or the gradient in the case of phi, and you will set these equal to 0, and that will lead you to an extreme point. And then hopefully one of those extreme points is a maximizer. Okay, so all right, so that's the usual thing. If you take the gradient with respect to j hat, what you will get is this thing c times phi minus lambda phi. So this is a vector expression, which is what you would expect when you take the gradient of this scalar function. And then the derivative with respect to the partial derivative with respect to the Lagrange multiplier is this thing 1/2 1 minus phi transpose phi. Okay, and then again, to find the extreme points, we set these to 0. So setting these to 0, now you can see why we incorporated this constraint the way we did, right? So at an extreme point of j hat, this derivative will be equal to 0. And if it's equal to 0, then that means the constraint is satisfied. Okay, because I basically recover the original constraint equation. Okay, so does that make sense? All right. So we set those to 0, and we get 2 equations. And what kind of linear algebra problem is this? So I have a matrix times a vector is equal to a constant times that same vector.
Eigenvalues?
Yeah, so this is an eigenvalue, eigenvector problem. Good. So when we did regression, we got a linear systems problem. when we do PCA, we get an eigenvalue problem that we have to solve. Okay, so this is, so I'll call this an eigenproblem. Phi star is the eigenvector of the matrix C, and lambda star is its corresponding eigenvalue. Notice that, so do I get the same phi that would maximize the original function? So you can see if I have an eigenvector and an eigenvalue, well, the eigenvector will satisfy this constraint. So the constraint term will be 0. So a maximum of the surrogate is the same as a maximum of the original function. Okay, so I haven't. So that's why the Lagrange multiplier and the constraint are incorporated the way they are. So they don't change the objective, and they incorporate the equality constraints in a very natural way. Okay. All right, good. So so I just all right. So now I have an algorithm. So I take my data, my original input, and then I compute the sample covariance. And the way it's been described here, I first mean center. So the sample covariance involves mean centering the original data. So by mean centering the original data, so as I formulated it, I'm assuming that X is already mean centered. But if you had unmean centered data and you're trying to do PCA, you would first mean center it. And then you would form this object C, which is the sample covariance. And then you calculate an eigenvalue and an eigenvector of the matrix C. Okay. Now, in general, the matrix C has many eigenvectors and eigenvalues, right? It doesn't have just one, so it might have more than one. Okay, but any of them is a solution to the problem that we've just described. It would be an extreme point of that that function J. Okay. All right. So so the next question, so everything we've done so far, this is just the mathematical setup. So formalizing the mathematical problem and then arriving at something to now solve. So a question is, how do I compute this? So there are existing eigenvalue and eigenvector solvers. So you can form the sample covariance explicitly and then call one of those. But in the same spirit as linear regression, forming this explicitly can lead to a matrix that is not well conditioned for the eigenvalue problem. So if you can solve the same thing without forming this explicitly, then that would be better. So there are ways to do that. And so a naive algorithm is you form C and then invoke the eigensolver. A different way to solve it is to use this magic tool from linear algebra called the SVD. Okay, so it turns out every matrix has an SVD, and this SVD will be a special factorization of the matrix that has a bunch of like very magical properties that help you solve problems. Okay, so the factored form I will write as U sigma V transpose. So the SVD is the product U sigma V transpose, where let's just assume a typical data matrix will have many data points and relatively fewer dimensions. It's not always true, but often. And in fact, the example we'll do Thursday, this will not be true, but it won't matter. But just schematically to have a picture in our heads, let's imagine that X is tall and skinny. If I let's let little s be the smaller of these two dimensions. Okay, so I'm going to define what the right-hand side is, and for that I'll need this parameter s. So s is the smaller of m and d. So our picture of s won't be accurate if x is not tall and skinny. So if it's short and fat. But the formulas will write down, those will all hold as long as I let S be the smaller of the two input sizes. Okay, so in this case, little s is D in the picture. Okay, so what's the right-hand side? U is going to be in this case, a tall and skinny matrix. And this matrix will have the special property that U transpose U is the identity. Okay, so it will have M rows and S columns. So in this case, S is equal to D. And U transpose U will be the S by S diagonal matrix. And U will give these a special name. We'll call these the left singular vectors. Okay. The matrix sigma will be a diagonal matrix, an S by S diagonal matrix. Okay, so and by convention, we will we'll label them sigma 0 through sigma S minus 1, since this is S by S. And also by convention, we will assume that they're ordered in non-decreasing order. So sigma 0 will be larger than sigma 1, or larger than or equal to sigma 1, and so on. And the singular values are also special in the sense that they will be non-negative. Okay, so the singular values will always be positive. All right. And then lastly, V will be another orthogonal matrix that is D by S. And we will refer to, so the matrix V will enter into the decomposition as V transpose. Okay, so I've sort of drawn, so think of, so this drawing, the little square you see here is V transpose. V itself is a D by S matrix, just like U was an M by S matrix. So V transpose is S by D. And I'll refer to V, so its columns, the columns of V, which are the rows of V transpose. The columns of V we'll call the right singular vectors. Okay. So this is, when you see this, you should be kind of amazed that this exists for any matrix. That's pretty cool because it has such a special structure. And you can see that this structure is something you can exploit. So if you replace X by this form and you're multiplying X's out, for example, X transpose X, then you can see, oh, well, there's orthogonal matrices. So just like the QR decomposition that we saw for linear regression, where Q kind of disappears when you plug it into X transpose X, then one of these is going to disappear as well. And you'll be left with the other. As you can imagine, because this is diagonal and you have vectors here, those will somehow be related to the eigenvectors and eigenvalues of the problem that we're trying to solve. Okay. All right. So and in fact, you can use the SVD also to solve the linear regression problem. So as an exercise to yourself, you might ask how to do that. And that's yet another algorithm for doing that. Okay. So just to summarize, this PCA, we have described it as a finding an axis that maximizes projections. To find that axis, we need to solve an eigenvalue problem. And the eigenvalue, it's an eigenvalue problem applied to the sample covariance of the data. And to solve this problem, we will use the SVD. So since C is equal to X transpose X, we'll plug the SVD in, and then a bunch of stuff will cancel. So if we do this substitution, then what you will find, so if you plug this SVD into the formula for C, and you do a little bit of algebra, you will get C times V is equal to V times this funny thing. Okay, so what is this? The funny thing, Okay, so the V's, these are vectors. So the V's, so the columns of V, those are all vectors. Sigma is diagonal. Okay, so sigma squared is also diagonal. It's just a diagonal matrix where you replace all the sigma or the diagonal entries with their squared entries. And then this 1/m, this is just a constant. It gets so the thing in parentheses is diagonal. And I am taking a matrix and multiplying it by a diagonal matrix. So V times the stuff in parens, which is just some diagonal matrix. So this matrix equation that you see here, if this thing is diagonal, then this thing we've written down is the same as a system of equations where each equation is the matrix C times one of the right singular vectors, okay, one of these V's, columns of the capital V, equals a constant times the same vector. Okay, so what is this saying? So we've just said, if you give me the SVD of X, then I can write down all of this, or I can write down a bunch of solutions to the eigen problem that I'm trying to solve. Okay, and those solutions are, you just take the right singular vectors. Each one of those is a candidate axis, and then and the eigen let's see, and then the eigenvalues, they're just formed from the singular values, squared and then divided by m. Okay. All right, so this gives me now a new scheme to solve the problem, which is, well, I have to calculate the SVD, but there are, there's linear algebra software that does that for you in a reliable way. So you would just invoke that and take the right singular vectors as the solutions. Okay, so all right, so are we following so far? Kind of. Okay. So we'll come back to this sort of interpretation question in a second. All right. Now, one question you might have at this point is like, okay, I have a bunch of these axes. In that original problem, I was just looking for one. So the fact that I have a bunch, what does that mean? Or like, what do I do with that information? Okay, and so for that, we will invoke another magical property of the SVD. This is the one that is like even more magical than what we've seen so far. Okay. This SVD, a different way to write this product is as the sum of the sum of a left singular vector times its corresponding singular value times the right singular vector, the corresponding right singular vector transposed. Okay, so remember these UKs and VKs, these are the columns of U and V, or VK this is actually a row of V transpose in our definition. And then this is just the singular value. Okay, so just sorry, maybe for this picture, so for each one of these, so there's a column, for each column of U, there's a corresponding column of V, which is a row of V transpose, and there's a corresponding singular value. Okay, and when I substituted them in, multiplied them out, I got this system, and you'll notice all the, each one of these equations on this right-hand side involves a right singular vector and its corresponding singular value. Okay, and the left singular vector has canceled out in this process of substituting it into C, but it was there at some point. Okay, so if I go back to this, the fact that sigma is diagonal and that U and V have the shapes as we've described them means that a different way you can write the left-hand side product is as this sum of vectors. And this is, notice this is a column vector times a row vector. So when I take a column vector times a row vector, what object do I get back? What is so if I take one of the UKs and I multiply it by VK transpose, what type of object do I get back?
Single value.
So someone suggested a single value. It's actually not a single value. What is it? Sorry about a column vector times a row vector. Okay, so the thing I get back is I get a matrix back. Okay, so that's just, you could think of that as being just the definition of a matrix product. The rank of that, what is the, so does at least one of you buy that? So I take a column vector times a row vector, I will get a matrix back. What is the rank of that matrix?
For free variables.
So I heard a vote for the number of free variables. Okay. So it's not quite that. It's even smaller than that. Okay, so that if I'm viewing the matrix as sort of a set of linear equations, or as coefficients of a set of linear equations, asking about the rank is the same as asking about how many independent linear equations there are. Okay. And how many will there be? In this case, if I just have one column vector times one row vector.
Is it K?
I'm sorry?
K.
So I have a vote for K. So if I'm just taking, so yeah, so if you might be thinking of a question that's a little bit ahead. So if I just take one singular or one vector UK and one vector VK, or let's just call it, a vector A and a vector B transpose, I multiply them. I'm saying I get a matrix. I'm asking about the rank of that matrix, so the number of independent equations that matrix identifies. And the rank is, it turns out, will be 1. Okay, and the way you can think about that is one way to view that product is you take, say, the row vector, think of those as the coefficients of some equation. That row vector is just going to get scaled by all of the different elements of the column vector. So there's really only one independent equation defined by that matrix. Okay, so anyway, if that isn't clear, you can ask offline or in the chat or refresh your memory. I think this is discussed in the linear algebra refresher material, so just go back and look at that. Okay, so what I'm saying is, going back to this, if I take this product, I rewrite it in this form on the right-hand side. So these are equivalent. And each one of these terms is a matrix of rank 1. Okay, so then if I am doing this sum over S terms, the maximum rank of this is going to be S. And in fact, if you compute the SVD in this way, and you retain only the only the positive singular values, and we'll always, I think in our definition, I forget, in our definition, I think this is a typo. This should be greater than 0. So if I take strictly positive singular values, then the number of singular values will turn out to be the rank of the original matrix. Okay, so all right. So this thing on the right hand side, the important thing to remember or to go back and understand later is how each one of these is a term of rank 1. And if the rank of the input is S, then this is what we call a rank S decomposition of the original matrix, because I've identified a set of vectors or a set of these rank 1. I've written the left-hand side as the sum of a bunch of rank 1 matrices. Okay. So in terms of the shape, so if I think of, so one of these UKs is a column of U, and this is a column of V, or a transposed. So this product will be an M by D matrix. So summing all of these results in a matrix of the same shape, M by D. Okay, and then let's see. Okay. So I guess, I get over. So under this definition, that the singular values are non-negative, not strictly positive. If the matrix has a certain rank R, then some of the last singular value that is positive, that will be the rank of the original matrix. Okay, that's not that important right now. Okay, so all right, so I have this decomposition. There's these magical properties. I can view the decomposition as a sum of rank 1 matrices. If I want to approximate the left-hand side, and I have this convention that I've ordered the singular values from largest to smallest, then if I just cut off this sum at some value little r, okay, so I pick any little r up to s. This thing on the right-hand side, it turns out, will be a rank R approximation of the left-hand side. Okay. And it's not just any approximation. So if I terminate this sum, instead of going all the way to s minus 1, if I go up to r minus 1, so I pick some r that is less than s, then what I'm saying is I've taken this decomposition and I've approximated it by a truncated version. So I take U and I keep only the first little r columns and I throw away the rest. And I do the same thing with V, and then I have to do the same thing with sigma to get the right shape. Okay, so if I just keep the top r singular values and their singular vectors, remember I've ordered the singular values from largest to smallest, then this will be a rank R approximation of the left-hand side. So I'm retaining the first R columns and the top R singular values. And not only is it a rank R approximation, it's actually the best rank R approximation for among any other kind of rank R approximation you could choose. So I could pick any matrix A and any matrix B where A and B have R columns, and then form, AR transpose BR. But it turns out there's no choice that will give an approximation that is better than truncating the SVD in a particular measure, which is If I take this rank R approximation and I multiply it out so that I get a matrix back, and I look at the sum of squared differences of all the entries. Okay, so that's a special norm called the Frobenius norm. Then that in that measure where I look at the difference, the truncated SVD is actually the best such rank R approximation. Okay, so if I have a matrix X and I compute its SVD and then I truncate the SVD, I just get rid of, like, instead of doing the full SVD, I just, I maybe calculate the first R singular values and singular vectors, and then I stop. That will be, the best approximation in some measure. Okay, so this gives me another. So remember, we're looking for some axis that is a good representation. Each singular vector that I take could be an axis, and in fact, I might retain, like, if I want to go from 17 dimensions to 2 dimensions, and I want to know, well, which of these singular vectors should I choose? Then this fact suggests that I should pick the top 2 singular vectors as my as the axes of my 2-dimensional representation. Okay, so that's all right. So we've done like a lot of kind of tedious stuff, and the punchline is, if I want to solve the PCA problems, I want to find some axes that sort of maximize or maximally preserve the variance in the original data under this data model that the data points like come from an ellipsoid type distribution. So a multidimensional Gaussian. Then I should calculate the SVD of the sample covariance and then keep the top R, say the top 2 singular vectors. Use those as my axes and then project onto those. Okay. All right. So, all right. Well, this is a good place, I think, to pause. Okay. So now in the notebooks for 15, if you haven't done them already, there are 2 parts. One part is about that data compression problem. And there, we are asking you to apply the SVD on its own, right? So remember that, so in the derivation that we've just done, we've derived a solution for the principal component analysis problem. And as part of that, we used this tool, which is the SVD. The SVD itself is a standalone tool. So one way to use it is, if you just give me any matrix and I want a good approximation to that matrix, then what you can do is you can just calculate its SVD and then truncate the SVD. And then your representation, so what's your representation now? So if I think of the image analysis problem, if I've taken if I've done an R truncated SVD, so I've kept the top R singular values and vectors, then instead of storing, let's say my image is 1024 by 1024. So instead of storing 1024 by 1024 pixels, if I interpret that pixel object as just a matrix of values, and I calculate the SVD, and I pick R to be like 20, let's say. So that means, remember the shapes of the SVD. So imagine now that X is 1024 by 1024. And now what I'm doing is, well, I picked R to be 20. So then that's like replacing this 1024 squared thing with something that is 1024 by 20. And then another thing that is 20 by 20, or sorry, 20 by 1024. And then these diagonal values, which, you know, there are 20 of them, right? If I pick an R to be 20. And so that will be, you know, that's just something that's like, you know, 40 times 1024 plus, you know, these 20 values of the diagonal. And now that is my new representation of an image that originally was 1024 by 1024. Okay, so that's how compression works in the image problem if you just apply the SVD as an off-the-shelf tool. Okay, does that make sense? Okay, I'm saying this because sometimes for the image compression one, people get confused and they try to do PCA on the image, but you don't need to do PCA there. There, the data is just the matrix of pixel values, and you can just apply it directly. It's only if you're doing this kind of variance analysis thing that you run PCA, and there you mean center the data, and then you apply the SVD. So that's the difference between these two settings, right? Okay. Now, and then the last thing for the image compression one, if you want to get the original image back, then you would have to take these factors and then multiply them out. And so that, you know, then you get 1024 pixels. You know, you could also just calculate them on the fly, like without multiplying out the whole thing. Anyways, question.
Do you think PCA packages actually use SVD, or do they use it? Because you said it's an approximation, right? Does that mean there's a bit of error?
Yeah. So the question was, do PCA packages actually use the SVD? And the answer is yes. I think standard ones do use the SVD. This truncation is something that you do optionally, right? So you can use the full SVD, in which case, you know, you don't compress anything, and your PCA, in that case, you don't reduce the dimensionality of the input data. But usually you're running PCA because you believe that, oh, my 17-dimensional input, really there's only 2 or 3 dimensions that effectively matter. And PCA with this truncation gives you a way to identify some lower dimensional representation. Okay, so when you call PCA, a parameter to PCA is, well, how many of these dimensions do you want to keep? So if you pick 3, then you will get a 3-dimensional representation. And if you ask, what is that 3-dimensional representation? Well, it's some choice of axes that are orthogonal. So you could even think of it as, you know, it's some 3-dimensional space defined by orthogonal axes that maximizes how much variance is retained in the projection.